And then you can tell me next week whether or not you feel like you want to run the camera. Incidentally, try not to bump the camera if you should happen to find yourself in this area. So here's the story. I hoped to have better notes put together, but I didn't get the notes put together last night, and so I'm going to kind of be winging this. We're going to do some chalk talk. Should be on par with what the notes we gave you. And then once you look at the notes, you'll hopefully be able to figure out what I just said. So last week, we left off, we just looked at the R-squared force. We said that for 2-point charges in space, force is equal to Q1 times Q2 over 4 pi E naught R squared. So, a couple of the key features of this law, again, just for redundancy, was that this describes a symmetric force field that emanates from a central point charge. Both of these guys are point charges, and so they both produce symmetric force fields. The magnitude of the force is dependent on the size of the charge. So you got Q in the numerator there. That means that as Q goes up, the size of the charge goes up, the size of the field goes up. And the field is what we call the forces exerted by one charge on another. So it makes sense that the larger the charge you have, the larger are the forces that are emanated from that charge. I want to describe this 4 pi r squared term one more time. The way that this works is that because these guys are the fields emanated by a point charge are symmetric around that charge. At any given r distance in space, the magnitude of the force is the same. The direction is not necessarily the same, but the magnitude is the same at every point on a sphere composed of radius r. Now, obviously, the smaller that sphere is, the closer you are to the charge, the more of that field that you're going to see. The R-squared force law takes care of that by noting that essentially, if you sit right on top of this point in space, you see all of the fields emanated by that charge, because you're right in the middle of them. But if you move a radial distance outside of that charge, it's as if all of the power or the fields exerted by that charge have now been spread out over a sphere that sits around that charge. And so if you're sitting at a point in space that is some radial separation distance r from that charge, it's as if now instead of seeing all of the charge, if you were right on top of it, it's as if you'd spread all of that charge out over the sphere, and all you see is that little infinitesimal point or bit of charge that is spread over the region of the sphere that you're located at. It's weird, huh? That's why in this equation we have the 4 pi r squared term. That's the surface area of a sphere. So we divide the total magnitude of the forces by the surface area of the sphere, and that's the same thing as saying essentially you spread all the charge out over the surface area of the sphere and you only see the little bit of charge that you're sitting right on top of. This describes a radial decay of the forces. You move out at a distance r, the fields diminish. Go ahead.
So does that mean like the farther you go out, the weaker it is?
The farther you go out, the weaker it is.
Okay.
Yeah, that's all that's saying. But the physicists noted that the geometric relationship, that it was as if the charge had been spread over a sphere. It diminishes in that fashion. Okay? Now, the E naught term right here. E naught is the permittivity of free space. It's a measure of how well the space that you're occupying allows fields to be communicated through it. You only use this E naught term when you've got empty space, free space that's not inhabited by any other matter. Now, what's true is that when fields have to pass through something other than vacuum, the magnitude of this goes up because fields they aren't communicated through matter as well as they're communicated through vacuum. And so if you're trying to transmit a field through space, but it has to move through matter, you can guarantee that the strength of that field is going to diminish as it passes through the matter. This is because matter interacts with fields. So we're going to be using this law to argue for the periodicity of the periodic table, the trends observed in the periodic table. Now, I've told you that this law only truly applies to a point charge. Here's the good news. When we go through what we're going through next and we're building up the periodic table, we're going to be working with systems where we're talking about one atom, and so all of the nuclear charge is tucked into the center of that atom, whether it's 2 protons, 3 protons, 4 protons, or whatever it is. The nuclear charge is always due to protons, right? Anyway, the nuclear charge is always in the center of that atom, and you only have one center of positive charge. And so, in reality, the fields that surround any atom are very symmetric, like this is. If you had a molecule where you've got a center of positive charge in one place and a center of positive charge in the other, you're not going to get this spherically symmetric decay of the fields. But in atoms, while it's not exactly spherically symmetric, because all of the positive charge is in the center, it's highly symmetric spherically. It's very close to being spherically symmetric. And we'll learn more about that in a second. The reason I'm telling you this, though, is because when we look at atoms, I want you to remember the key features. The larger the charge is, the stronger the force is. The closer to you are to that charge, the stronger is the force. And as you move away from that charge, the forces diminish with distance. What's true for the point charge is largely parallel in the discussion of atoms. Okay? And so now we're going to start talking about what makes an atom. When we get on to lecture next week, we're going to go into light and matter, the subject of light and matter. And when we do that, we're going to look at the Bohr model of the atom just a little bit closer. In the Bohr model of the atom, we'll actually run through a calculation that shows you how to derive the equations that Bohr derived that actually predicted the emission spectrum of the hydrogen atom, what wavelengths of light would be emitted from an excited state hydrogen atom. When we do that discussion, we're going to note that Bohr made a couple of postulates, a couple of assumptions, and one of those assumptions was that in this atom you have is this the one? Where's is it B squared over R? You have an equality between the magnitude of the electric forces between the positively charged nuclei and the negatively charged electrons. So if you've got a center of positive charge here and you've got electrons in orbit around it, there's going to be attractive forces that bind the negative charge to the positive charge in the center. So there's attractive forces that do this. Bohr made the assumption that those attractive forces that bind the electrons to the nuclei would be exactly equal to the forces required to hold an orbiting object in stable orbit. You take a mass and you stick it on a string and you wave it in circles. Well, the mass doesn't go flying out, it's tethered by the string. In order for that to happen, in order for the mass to stay in orbit by that string, there has to be an inward acceleration pushing that mass towards the center of its orbit. Otherwise, the mass will go flying off into space. Well, what binds an electron to the atom is the balance, or one of the things that happens in the binding of electrons to atoms is a balance of that force required to keep the electron moving inward, accelerated inward, that ends up being generated by the electric force. So you've got a force inward required for stable orbit, and it's going to be provided by the electric force. And so what we just said then is that it's that the positive attractive electric forces that keep that orbiting electron bound to the nucleus. We'll get into this more. This isn't the point of the lecture we're doing now, but since we're building atoms, I figured I may as well let you know, let you see that in advance. Bohr made another assumption. Go ahead.
Why is it R7?
Oh, that's R squared.
Okay.
Sorry, that should be R squared. This is why there's a difference between when I actually get the notes generated in advance and when I chalk talk, because when I chalk talk, you can't read what I've written. If I get them in advance, then it's, you're reading a Word document instead of my chicken scratch. Another assumption the board made, and again, we'll touch on this more in coming lectures, was that they noticed right around the time that Bohr ran the equation for the hydrogen atom, they figured out that matter was a wave. They knew that light was a wave. So you take photons, you throw them against a diffraction grating, and you get a diffraction pattern, right? And it's because the photon actually isn't a point in space. It spreads out over a volume of space, and it occupies all of those volumes at the same time, like a wave. It diffracts. Well, shortly after that, they found out that electrons did the same thing. So it's not just photons that travel as waves, it's electrons that travel as waves also. So Bohr noted that, and he made some assumptions, and we'll see next week that he came out with a calculation that very accurately predicted excited state energies of atoms. So what you need to know then is that an atom is negatively charged electrons bound in orbit by their attractive forces to the nuclei, and that these things are not necessarily points in space, they're waves that spread out over whatever volume of space is being occupied by the electron. All right, we're going to take those things, and now we're going to start building atoms. But to build the atoms, we're going to need an additional piece of information. And I'm not sure that the image that I draw you is going to be the best way to do this, but I don't know of any other way to do it. At least I can't think of any off the top of my head. You need to understand that, first of all, we said an electron occupies a volume, right? So it's not an infinitesimally small point in space. It's a volume of space occupied by this negative charge. Well, because of that, there's only so many electrons that you can fit outside of a nuclear center before the volume just outside of the nuclear center becomes full. Here's a way to think of this. Let's take a basketball, right? Maybe basketball isn't the best analogy, but take a basketball. And now we're going to take a bunch of tennis balls. And I'm going to do this in 2 dimensions, but imagine that I'm doing it in 3 dimensions. I'm going to start putting these tennis balls around the basketball. Well, eventually, I'm going to run out of room for tennis balls. I'll have surrounded that basketball by as many tennis balls as I can possibly fit outside of the volume of a basketball. And at the point that I fit just as many tennis balls as I can outside of that volume of the basketball, if I want to stick more tennis balls in orbit around the basketball, I'm going to have to move them out to larger radial separation distances. Does this make sense? Right? This is just a geometric argument. That's all that is. Well, you can almost think of your electrons as tennis balls. They're not infinite points in space. They occupy volume. Every electron has its own associated volume. And so in chemistry, to understand the periodic table, you've got to understand what's introduced to you as shells, but is derived from these volume requirements. When you are in really close to a nuclei that has no other electrons around it yet, I don't know how many positive charges it has in the center, it doesn't matter too much, but let's just draw a nuclei. You have a bunch of protons in the nucleus. When I first start trying to pack electrons in around this nuclear center, I can only fit 2. There's a volume outside of this nuclear center that is only large enough to fit 2 electrons. Once you've put 2 electrons inside that volume, you can't fit any more. Once I move just external to that volume, there's going to be another volume available. In that volume, I'm only going to be able to fit 8 electrons. Once I fit 8 electrons outside of that volume, it's going to be the situation where I can't pack any more electrons outside of it. If I want to keep piling electrons onto this nuclear center, assuming that it has a positive charge yet.
So the second formula, is that matrix electrons?
Which formula?
The MR squared over.
Oh, this one, all we're talking about, I just threw that equation up right now to remind you that what binds the electron is the balance between, you've got the centripetal acceleration that has to be provided by the attractive force between the electron and the nuclei.
Okay.
And that essentially is what binds the atom. We don't have to know that to understand the shell concept, but they do complement one another.
All right.
So the first shell, that first volume outside the nucleus, you're only going to be able to fit 2 electrons. If you want to keep packing electrons on, you got to go 1 shell out. That next shell can pack in 8 electrons. You fill up that shell, you still need room, you're going to have to go 1 more shell out. It turns out that shell can pack 8 electrons into it. Now, assuming that you still have enough positive charge in the nuclei to continue attracting electrons, if you want to keep putting electrons on, you got to be moving even further out with this next shell. Now, I want you to notice something. If you're thinking about an onion and you're looking at the concentric skins that fall on the onion, the ones that are out towards the end of the onion, not the center, the ones that have the largest radial distance, have the largest amount of surface area, right? You pull out a skin from the inside, it's going to be really tiny. You pull out a skin from the outside, it's going to be much larger. Well, it turns out that because these shells are growing in size, they begin to be able to accommodate more electrons. So once you get out to this third shell here, now you can fit 18 electrons. The shell after that, I think you get 18 electrons. So that concept is hopefully going to be able to help us to understand why the periodic table displays periodic behavior. Its name is the periodic table because there's a certain periodicity in the behavior of the elements, and that periodicity is largely to blame for, or is caused by these geometric constraints on the space that's occupiable by electrons. And here's how this works. I want to say this. While I've drawn these shells as having a fixed size, it is not true that these shells necessarily have a fixed size. When we move across a row in the periodic table, we're going to see that the shell sizes actually contract. Let's see if I can make this clear with an image. So we're going to begin with, we'll start with the lithium atom. We'll start working with the lithium atom. Lithium has 3 protons in its nucleus. So for a neutral lithium, you've got 3 protons, 3 electrons. The electrons and the protons balance each other out. Now, lithium's got those 3 protons, and we've occupied the first shell with 2 electrons, one there, one there. And for the neutral atom, we're going to want 1 more electron, and we're going to say that that electron has to sit in this next outside shell. So in this next outside shell, we have 1 of 8 total electrons that we can fit into, right? We can fit 8 electrons in that shell if we need to. Right now, we've only got 1. So we go from lithium, I'm the worst chemist in the world. Anybody got their periodic table in front of them? Lithium to beryllium, is Be the next one? What's the next atom element in the periodic table? Shh, don't tell me that. Yes, it's beryllium. I'm the dumbest chemistry instructor you're ever going to have, and the smartest. All right. So when we're moving from lithium to beryllium, to do so, we've got to add 1 more positive charge to the nucleus. I'll say this once and twice and 3 times. It's always the number of protons in the nucleus that determines the atomic identity, because it's the amount of positive charge in the nucleus that determines how much negative a charge can be attracted by the atom. So to go from lithium to beryllium, this guy's lithium right here, we're going to have to add 1 more positive charge to that nucleus, and assuming that it's a neutral beryllium, we'll add 1 more electron. So let's stick our 4 protons now in this nucleus. 4 protons. The nucleus, we've got 2 electrons sitting in the first shell. I didn't draw this very well. I'll do it this way. So I'm going to draw this as yet unclosed shell out here. 1 electron in it, room for 8 more. Now, when we stick that additional positive charge into the nucleus, what is going to be the effect on the magnitude of the forces? R squared force law says that the force is directly proportional to the charge. So if we up the charge by 1, we're increasing the forces. Well, this does something. This next electron that we stick in there gets to approach, because it's in the same shell, at approximately the same distance as this electron here. So it moves in and scoots up next to the nucleus. But now the forces being exerted by that nucleus, because the nuclear charge is higher, the forces are larger, and what that means is that the forces on both of these electrons in this shell become greater. With greater forces, the electrons get pulled in closer to the nucleus. They get pulled in even tighter. And so by adding that additional proton to the nucleus, by increasing the positive charge, you increased the strength of the forces, and you caused the entire nucleus to contract. It got smaller. So it would have been better for me to have drawn a smaller blue circle on the lithium than on the beryllium. Right? Now, we go to the next one. We have boron we got to build next. To build boron, we're going to throw 1 more positive charge in the nucleus, 1 more electron on top. But the same thing's going to happen. The increased amount of positive charge in that nucleus is going to effectively pull all of the electrons in closer. And so now we'll have an even smaller outside shell for this guy. And it'll have 3 electrons in it. Well, guess what? As you move across a row in the periodic table, this trend keeps happening. You add one more positive charge, all of the electrons in that shell are affected by the increased forces, and they're pulled in tighter to the nucleus. And so atomic size ends up decreasing as you move from left to right across the periodic table, because the increased forces due to the nucleus pull all of the electrons in tighter. And with stronger forces, we have that atom type, whatever that next atom type that we just built, is better at hanging on to electrons than was the atom type before it. So your lithium atom, because its electrons are further removed from the nucleus, largely because of that, there's other things in play too, we'll describe in a second. Because its electrons are not able to have as close a nuclear approach, and because the nuclear charge is smaller, this atom type does not hold on to its electrons very well. The next atom down, beryllium, holds onto its electrons a little bit better. Boron holds onto its electrons even better. Closer approach, higher nuclear charge. So the magnitude of the forces, remember, are dependent both on the absolute charge and the approach. So if you got higher charge plus the atom contracts and you get a closer approach, you've got better binding forces all around. And so you move from left to right across the table. Nuclear charge is increasing, atomic forces are increasing, the strength that atom the strength with which that atom is able to pull onto charge increases. Now that explains the difference between metallic and non-metallic behavior. We're going to tell you, you look up in a Gen Chem textbook, they're going to tell you the metals are the first two columns, or not the alkaline earth metals, they get special names. They're going to tell you that metals are on the left-hand side of the table. Well, what a metal is in chemistry, the reason we call something a metal is because it doesn't hold on to its electrons very well. Metals give up electrons very readily to other atom types. Well, you now know why. It's because they have the least amount of nuclear charge per electron that they're trying to hold on to. And they have the largest radiuses, and so those electrons can't get close into that nuclear charge. When you get all the way to the right-hand side of the table, and you're dealing with things like fluorine, chlorine, bromine, iodine, those guys have the strongest nuclear charge of whatever row they're in. And so they're binding or pulling on those electrons with the strongest forces. We call those nonmetals. The atom types that have the strongest pull on electrons are the quote-unquote nonmetals. We'll get into consequences of pairing of the metals and nonmetals and stuff like that later. For right now, though, remember that building up atoms from left to right increases forces, atomic sizes contract. Now something weird happens. This gets funny. I'll show you in just a second here after I take a sip of my Pepsi. We're gonna keep moving across that row in the periodic table. Drew boron there. Let's skip a few. Let's go all the way to fluorine. See what F is? It's element number 9. We got 9 protons on that thing. 2 of them are tucked in the inside shell, that first shell, and the other 7 are sitting in the outside shell. So draw that real quick here. This guy here. A couple electrons here. And now you've got a really, really, really tiny and contracted second shell that's got 7 electrons in it. When we stick one more electron in that shell, so this was fluorine, we stick one more in, we've got a neon atom. Now your neon has 8 electrons in that shell. if we want to stick one more electron onto a neon atom, we're going to run into a problem. Neon is called a noble gas. You guys have heard this before? Noble gases are noble because they're not